We started our second unit in calculus with a review of how to find slope and a reminder that it is a rate of change. We then examined a couple different rates of change, one being the instantaneous and the other being the average. We learned that they are different but also related by taking a limit. And today we're going to connect all those concepts and learn about a very important idea in calculus called the derivative. In fact, it's one of the two most important concepts, the second being what we call the antiderivative or the integral. But today we're going to build our foundation off what we know about rates of change to define the derivative. So our learning target for today is we will define derivative analytically as the instantaneous rate of change, which is the limit of the average rate of change. The second sentence in our notes is a definition of the derivative, and it's also packed full of synonyms that we'll need to be aware of when we read them as context clues that are taking us back to the derivative. So the derivative of a function is the slope of the tangent line and the instantaneous rate of change. So when you see any four of those terms, derivative, slope, tangent, or instantaneous rate of change, they're all referring back to what we know as the derivative. At the end of that definition is the formula for instantaneous rate of change. And remember from our last lesson, it actually starts with the difference quotient of the average rate of change and only becomes the instantaneous rate of change when you put the limit statement as x goes to c in front. So what we'll call this formula is the specific derivative formula. So it gives us the derivative of a function at a specific value c, and that c is an x value. A little bit later in this lesson, we're going to look at the general derivative formula as well. Let's look at an example of how to find a specific derivative of a function. It asks us for the derivative of the function x squared at x equals 0. So that specific value 0 is going to be the value of c in our formula. It's a good habit to copy down your formula a few times until you're comfortable. And once you know that formula by heart, you can go ahead and jump into evaluating it at your specific c value. So what I did was I took our formula, and everywhere I saw a c, I substituted in the 0 value for c, and let's evaluate from there. I need to substitute everything into my difference quotient as it reads. So where you see the f of x, you're going to copy the function, which is x squared, minus f of 0, so that's the function value at 0. So we substitute 0 into our function for x. That gave me 0 squared. That follows the minus. And the denominator of our difference quotient, we still have x minus 0, and you can simplify that to 0, or just to x because the 0 goes away. And let's go ahead and keep continuing to bring our limit statement until we're ready to evaluate. So once I got rid of the 0 squared and 0, I was left with x squared over x, which of course reduces if you cancel out 1x in the denominator with 1 in the numerator. So we still have the limit as x goes to 0 of just x now. And of course, when we substitute that 0 in for x, we get a limit of 0. I know that answer of 0 doesn't sound like a very exciting answer, but I think it's one that we can look at in context visually, and it'll make a strong connection with what the derivative actually means. So we go back to our definition. The 0 that we found is actually the slope of the tangent line at x equals c. And remember, c was 0. And I picked a very basic function that we're all familiar with, the x squared parabola. And if you look at x equals 0, the tangent line is a perfect horizontal tangent. It has a slope of 0. So I hope that makes the connection for you from the instantaneous rate of change limit value to the slope to the tangent line on that parabola at x equals 0. I mentioned earlier that there's also a formula for the general derivative, and I'd like to show you how to derive that formula from what we know about average and instantaneous rate of change. But I'd also like you to know that it's valuable to have this formula because sometimes we don't just want the derivative at a specific value. We'd like the derivative for the entire function at any x value that we wish to evaluate. As we start looking at where the general derivative formula comes from, I think it'll help us to have a visual to refer to because there's a lot of variables in this short proof. But when we talked about average rate of change in our last lesson and started to turn it into the instantaneous rate of change by putting the limit in front of it, we had these x values of a and b, which we were imagining were getting closer to each other or converging upon a single point. Mathematicians quickly realized that that didn't make a lot of number sense, so they substituted a variable x for a, and so this value of b would then just be x, which is this x value, plus some difference, so they called it h. So h is the distance between a and b. That change is what you're going to see from this line to the next line in the proof. So all of the a's got replaced by the single x's, and all of the b's in the formula got replaced by the quantity x plus h. When you take a closer look at our new limit statement, it has a lot of variables in it, and hopefully you can see that it can be simplified by taking away x from both sides of that limit expression. And when you do so, you end up with this h left going to x minus x, which gives you 0. The other simplification that happens is in the denominator, we have a positive x followed by a minus x, so that x gets canceled, and we now just have an h in our denominator. So what you're looking at here, the limit as h goes to 0 of f of x plus h minus f of x over h is the difference quotient that we call the general derivative. And this is the derivative that you find for a function, and it holds true for all x. So once you have that formula for the function, you can substitute any x value, and it gives you the correct derivative for that x value. So let's take a look at an example of finding the general derivative for, we're going to use the same function, f of x equals x squared. Notice that it says find the derivative of f of x equals x squared for all x. That's our context clue that we're finding the general derivative. In contrast, in the first example we did today, it said to find the derivative at x equals 0. So that told me it was a specific derivative formula instead. So again, I'm going to suggest that you write down the formula enough times to where you're comfortable and you have it memorized. And I'm pretty sure you worked with it in your math analysis class, so I hope it looks familiar and you're well on your way to having it memorized. And our job moving forward, we're going to carry our limit statement. We're going to have to evaluate the function at both x plus h and at x. The one that's more difficult, of course, is this f of x plus h. So what we're doing is we're taking that quantity x plus h and we're substituting it into the function where the x is. So it becomes the quantity x plus h squared. Then we're going to take the minus from our formula and follow it with the function of x, which means you just copy this x squared, and then all over h, our denominator. We need to be careful when we square out our binomial x plus h, because when you square a binomial, you actually get a trinomial, x squared plus 2xh plus h squared. If you need a little side work for that, you could write x plus h times itself and do your FOIL, your first, outer, inner, last, and make sure you get all three terms of that trinomial. So then we're going to remember our minus x squared. And when you look at the entire numerator, I hope that you see that the first x squared minus x squared are going to cancel. Once those x squareds cancel, we can see that both of the terms in our numerator have an h, so we're able to reduce both of those terms by h, and we can only do that in a numerator if all the terms in the numerator can be reduced by the h. Another way to look at that, and I'll show it in my next step, is you can actually factor out an h and cancel it with the monomial h that way. So here I've factored out the h out of both terms in the numerator. I'm going to cancel that h with the h in the denominator. So I still have my limit as x goes to 0. I now have 2x plus h left. And when I am ready to substitute that 0 for x, that 0 for h, oh no. Sorry, I had to go all the way back to my second step. Somehow, magically, my h turned to an x in that second step. So hopefully you caught that and you didn't have to make all those corrections too. But let me try again. As h goes to 0 in this expression, substitute the 0, we get 2x as our limit. And what that answer of 2x means is it's basically a formula for the derivative of that function x squared for all x. So we can plug any x we want to, such as 0, and we get the same answer we did for the specific, which is 0. See you in class.